Tonight, we gently drift into the vast and silent expanse of the universe, a place so immense that even light itself takes millions of years to travel between its distant corners. As you begin to relax, allow your breathing to slow and let your mind soften. There is nothing to rush, nowhere to be, only the quiet story of existence unfolding slowly. The universe was not always filled with stars or galaxies or planets. In the beginning, there was only darkness, a silence so complete that even time had not yet begun in the way we understand it. Then, something changed, a tiny moment so brief and so powerful that everything we know began to expand. This moment is often called the beginning, the birth of the universe. The universe is about 13.8 billion years old, yet it began from something smaller than a grain of sand. That is not a poetic exaggeration. Current understanding suggests that everything we can see, everything we have ever touched or tasted or measured, all of it emerged from an extraordinarily small, extraordinarily hot starting point. Scientists call this the Big Bang, though it was not really an explosion in the way we usually imagine. It was more like the sudden appearance of space itself. There was no empty room that it expanded into. Space and time both began at that moment. In the very first fractions of a second, conditions were so extreme that the physics we know today did not yet apply. The universe was a dense, brilliant sea of energy, far too hot for even the simplest particles to hold themselves together. Everything moved at speeds we cannot truly picture, in a space so small we have no easy comparison for it. And then, very quickly, it began to cool. Cooling is one of the great quiet forces in cosmic history. As the universe expanded and temperatures dropped, new things became possible. Particles could form, then atoms. Then, over vast stretches of time, clouds of gas could gather together, slowly, pulled by gravity, until they grew dense enough to ignite. That is how the first stars were born. And inside those stars, something extraordinary was happening. The light elements that existed after the Big Bang, mostly hydrogen and helium, were being fused together under enormous pressure and heat to create heavier ones: carbon, oxygen, iron, the building blocks of planets and oceans and living things. Every element heavier than hydrogen and helium that exists in the universe today was forged inside a star, or in the violent death of one. Which means the calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was made inside ancient stars that lived and died long before our sun was born. You are not separate from the universe, you are made of it. Light takes time to travel, and that means looking into the sky is looking into the past. When you glance up at the night sky and see a star, you are not seeing that star as it is right now. You are seeing it as it was when the light you are receiving first left it. For nearby stars, that might be just a few years ago. For others, it could be hundreds or thousands of years. The Andromeda Galaxy, the nearest large galaxy to our own, is so far away that the light reaching your eyes tonight left it about 2.5 million years ago. At that time, our ancestors were still learning to make stone tools on the plains of Africa.
When astronomers point their telescopes at the most distant objects ever observed, they are seeing light that has been traveling for over 13 billion years. They are looking almost all the way back to the beginning. In a sense, the universe is its own archive. The farther you look, the older the story you are reading. There is something very restful about this idea. The past does not disappear. It travels outward as light, carrying information across unimaginable distances, quietly, patiently, without any hurry. The universe keeps its records in light. Space is not empty. It is full of a quiet energy that no one fully understands. For a long time, scientists assumed that the space between stars and galaxies was simply nothing, a vacuum, a blank stage on which the objects of the universe performed their movements. But measurements taken over the past few decades have revealed something strange and wonderful. The universe is not only expanding, it is expanding faster and faster over time. Something is pushing it outward with increasing speed. Scientists call this dark energy, though the name is more of a placeholder than an explanation. It is called dark because it does not interact with light in any way we can detect. It is called energy because it seems to be doing work, accelerating the expansion of space itself. And the remarkable thing is how much of the universe it appears to be. If you add up everything we can see and measure, all the stars and planets and gas clouds and black holes, it accounts for only about 5% of the total content of the universe. Another 27% appears to be a kind of invisible matter we cannot see but can detect through its gravitational effects.
The remaining 68%, the majority of everything, is this mysterious dark energy. The universe is mostly unknown to us, even now. That is not a discouraging fact. It is an invitation. It means the cosmos is larger and stranger and more layered than anything we have yet imagined. And every generation of curious people adds a little more to the picture. Gravity is the gentlest of the fundamental forces, and yet it shapes everything. Of the four fundamental forces that govern how matter and energy behave, gravity is by far the weakest. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. At the scale of individual particles, gravity is almost irrelevant compared to the other forces, and yet gravity is the architect of the cosmos. Over large enough distances and long enough timescales, gravity wins. It pulls clouds of gas together until they ignite as stars. It gathers stars into galaxies containing hundreds of billions of members. It shapes the large-scale structure of the universe into a vast cosmic web of filaments and voids. Gravity is patient. It works slowly, steadily, without interruption. It does not push. It does not rush. It simply draws things together, over and over, across billions of years, until something new emerges. Every planet, every solar system, every galaxy is the result of gravity doing its quiet, persistent work. There is something deeply calming about that image, the universe assembling itself, not through violence or urgency, but through the gentle, inescapable pull of matter toward matter, slowly, over time, without effort. Stars spend millions or billions of years in a state of perfect balance. A star is, in one sense, a long and peaceful standoff between two forces. Gravity pulls inward, trying to collapse the enormous mass of gas at the star's core. The nuclear fusion happening at that core pushes outward with enormous heat and light and radiation. For most of a star's life, these two forces are in equilibrium. Neither wins. The star simply shines steadily in that suspended balance. Our own sun has been doing this for about 4.5 billion years.
It will continue doing so for another 5 billion or so. Day after day, year after year, century after century, it burns with the same steady patience, maintaining a balance so precise that life on Earth has had time to emerge, evolve, and look up in wonder.
When you feel the warmth of the sun on your skin, you are receiving the product of that balance. Energy released from the fusion of hydrogen into helium at the sun's core, traveling outward through layers of gas over thousands of years, then racing across 93 million miles of space in about 8 minutes to reach you. The sunlight touching your face is ancient, and it was made in a place of perfect equilibrium. The Milky Way is so large that light takes 100,000 years to cross it. Our galaxy is a spiral, a slowly rotating collection of roughly 200 to 400 billion stars. If you could see it from far above, it would look something like a softly glowing pinwheel, with long curved arms of stars and gas wrapping around a bright central core. We live in one of the outer arms, about halfway between the center and the edge. The distance from one side of the Milky Way to the other, measured in the speed of light, is approximately 100,000 light-years. That means if you could travel at the fastest speed in the universe, 300,000 kilometers per second, it would still take you 100,000 years to cross from one edge to the other. Our Sun completes one full orbit around the center of the Milky Way, roughly 230 million years. The last time our solar system was in the same position in the galaxy, dinosaurs had only recently appeared on Earth. And the Milky Way is just one of an estimated 2 trillion galaxies in the observable universe. The scale of the cosmos is so far beyond ordinary experience that the mind, trying to grasp it, eventually relaxes. It cannot hold numbers like these. And there is something comfortable about that. Some things are simply too vast to worry about. Neutron stars are among the densest objects in the universe, and they spin impossibly fast. When a massive star runs out of fuel and collapses, the result depends on how much mass was involved. If the remaining core is dense enough, but not too dense, it becomes a neutron star, an object perhaps 20 kilometers across, roughly the size of a city, but with a mass greater than our entire sun. A single teaspoon of neutron star material would weigh about 10 million tons on Earth. Neutron stars are also some of the fastest spinning objects we know of. Some rotate hundreds of times per second, flashing radio waves or X-rays with such regularity that when astronomers first detected them, they briefly thought they might be signals from an intelligent civilization. They are called pulsars, and their pulses are more regular than the finest clocks humans have ever built. There is something oddly peaceful about a pulsar, a dense, quiet, ancient object spinning in the dark, sending out its steady pulse across light years of space, keeping perfect time for millions of years with no audience and no purpose, just the rhythm of its spin beating out into the silence. Black holes are not vacuums that suck things in, they simply wait. Much of what popular culture says about black holes is not quite accurate. They do not roam through space devouring everything around them. They do not pull things in with any special hunger. A black hole is simply a region of space where gravity has become so strong that nothing, not even light, has enough energy to escape. It exists because an enormous amount of mass has been compressed into a very small space, and like any massive object, it attracts other matter through gravity. If our sun were somehow replaced by a black hole of the same mass, Earth would not be pulled in. The planet would continue orbiting at the same distance, just without sunlight, in the same way it orbits the sun now. The gravity would be identical. Black holes are patient. They do not chase. They simply exist at the center of their gravitational influence, curving space around themselves, waiting for matter to come close enough to fall. At the centers of most large galaxies, including our own Milky Way, there are supermassive black holes containing millions or even billions of times the mass of a star. The one at the center of our galaxy is called Sagittarius A star, and it is about 4 million times the mass of the Sun. It sits there, quietly, at the heart of the galaxy, while 200 billion stars orbit around it over hundreds of millions of years.
Sound is a wave, a vibration that moves through a medium. On Earth, that medium is usually air or water or solid ground. The compression and rarefaction of molecules carries the wave from its source to your ear. In the vacuum of space, there is almost nothing to compress. The space between stars contains only a few atoms per cubic meter, far too sparse for sound waves as we know them to propagate. The universe, for all its violent processes, is silent to any ear that might listen. Supernovae, which are among the most energetic events in the known universe, release as much energy in a few seconds as our sun will release over its entire lifetime, and they happen in complete, absolute silence from any distance. Stars are born and die in silence. Galaxies collide over hundreds of millions of years in silence. The deep, quiet dark between everything is profoundly, perfectly still. There is a kind of rest in that. No noise, no urgent signals, just the slow movement of matter and light through an unimaginably large and utterly silent space. The observable universe has a horizon, and beyond it we simply cannot see. Because the universe has a finite age and light travels at a finite speed, there is a limit to how far we can observe. Beyond a certain distance, light simply has not had enough time since the Big Bang to reach us. This is called the cosmic horizon, or the edge of the observable universe. It sits at a radius of about 46 billion light-years in every direction from Earth. Notice that this is not the edge of the universe itself. It is the edge of what we can currently see. The universe may extend far beyond that horizon, perhaps infinitely, filled with more galaxies and stars and planets and possibilities. We are at the center of our own observable bubble of the cosmos, not because we are special, but because light has had the same amount of time to reach us from every direction. Every observer anywhere in the universe would see themselves at the center of their own similar bubble. The universe is vast in ways that even the word vast cannot hold. And yet, here you are, inside it, small and warm, resting. Cosmic voids are enormous regions of space containing almost nothing, and they are deeply peaceful. Between the great filaments and walls of galaxies that make up the large-scale structure of the universe, there are vast regions called cosmic voids. These are roughly spherical regions, sometimes hundreds of millions of light-years across, where very little matter exists.
The largest known void, called the Boötes void, is approximately 330 million light-years in diameter. If our galaxy were located inside it,
Ancient humans would not have discovered any other galaxy until the development of modern telescopes, because the nearest galaxy outside the void would have been invisible to the naked eye. Voids are not truly empty. There are still a few galaxies scattered through them, and the usual dark matter and dark energy permeate them. But they are the quietest, most undisturbed regions of the universe. Nothing much happens in a void. There are no cosmic collisions, no dense star-forming regions, no dramatic events. Just gentle, empty space, expanding slowly, waiting patiently for billions of years to pass. The universe makes room for places of profound rest. Water exists throughout the universe, carried by comets and clouds of gas between the stars. Water is not unique to Earth. It is one of the most common molecules in the cosmos. Clouds of water vapor and ice exist in interstellar space, in the cold regions between stars, where temperatures drop to just a few degrees above absolute zero. Comets carry water ice from the outer edges of solar systems. Moons of giant planets, like Europa orbiting Jupiter, are believed to have vast liquid oceans beneath their icy surfaces. In 2011, astronomers discovered a massive reservoir of water vapor surrounding a quasar, an extremely active galaxy core about 12 billion light-years away. The reservoir was estimated to contain 140 trillion times the amount of water in all of Earth's oceans combined. 12 billion light-years away, before Earth existed, before our sun was born, water was already there, drifting in an enormous cloud through ancient space. The building blocks of what we associate with life, with oceans and rain and rivers and the feeling of water on your hands, those molecules are woven throughout the universe. They do not belong only to Earth. They belong to everything. Every second, the sun converts about 4 million tons of mass into pure energy. Inside the sun's core, hydrogen nuclei are fused together under pressure and heat to form helium. In this process, a tiny fraction of the mass of the original particles is converted directly into energy, according to Einstein's famous relationship between mass and energy. The amount is small in proportion, just about 0.7% of the mass involved. But the sun is so large and the process so continuous that 4 million tons of matter disappear every single second. That is 4 million tons turned into light and heat and radiation, streaming outward in every direction into space. The fraction that reaches Earth drives almost all life on this planet, the photosynthesis that produces oxygen and feeds the food chains, the weather systems that move water around the planet, the warmth that keeps the surface from freezing, all of it powered by a small fraction of the energy released when hydrogen becomes helium, in a process that has been running continuously for 4.5 billion years. The sun is steady and generous. It does not calculate what it gives, it simply shines. Galaxies can pass through each other and almost nothing collides. Galaxies are not solid objects, they are collections of stars separated by vast distances. Even within a galaxy, the space between individual stars is immense. When two galaxies collide, as our Milky Way and the Andromeda Galaxy will in about 4.5 billion years, the stars within them almost never actually hit each other. They pass through the spaces between each other like two swarms of fireflies merging in the dark. The galaxies will distort each other's shapes with gravity. Stars will be flung into new orbits. Gas clouds will collide and compress, triggering bursts of new star formation. The overall structure of both galaxies will be disrupted over hundreds of millions of years, gradually merging into a single, larger galaxy. And yet, in all of that vast, dramatic process, the probability of any two individual stars actually colliding is extraordinarily small. The universe is full of events that look violent from a distance, but are, at the scale of individual objects, barely touching. Two galaxies can merge, and most stars within them will never know. There are more stars in the observable universe than grains of sand on all of Earth's beaches. This is one of those facts that sounds like exaggeration but holds up to careful estimation. Astronomers estimate there are roughly 2 trillion galaxies in the observable universe. Each galaxy contains an average of perhaps 100 billion stars, though many contain far more. Multiply those numbers together and you get a figure somewhere around 200 sextillion stars. That is a 2 followed by 23 zeros. Geologists and mathematicians have estimated the number of grains of sand on all Earth's beaches and deserts at roughly 7.5 quintillion, a 7 followed by 18 zeros. The number of stars in the observable universe is tens of thousands of times greater than all the sand grains on Earth. And each of those stars is a sun. Many have planets. Some of those planets may have liquid water. Some may have conditions hospitable to chemistry as complex as what produced life here. The odds that anything of interest happens anywhere in the universe feel overwhelming. And yet here we are, on one small planet, looking out. Time passes differently depending on how fast you move or how strong gravity is around you. One of the most astonishing discoveries of modern physics is that time is not the same everywhere. Einstein's theory of relativity showed that time passes more slowly for objects moving very fast, and also more slowly in stronger gravitational fields. These are not just mathematical abstractions, they are measurable, real effects. The GPS satellites orbiting Earth move fast enough and sit far enough from Earth's stronger gravitational pull that their clocks drift relative to clocks on the surface. Engineers must account for these relativistic effects in their calculations, or the positioning systems would become inaccurate within minutes. For an astronaut orbiting the International Space Station at roughly 28,000 kilometers per hour, time passes very slightly slower than someone standing still on the ground. Over a long mission, this adds up to a measurable difference of fractions of a second. Near a black hole where gravity is extreme, time slows dramatically compared to what a distant observer experiences. An object falling toward the event horizon of a black hole would appear from outside to slow down and eventually freeze, its clock ticking more and more slowly as it approached. Time is not a rigid backdrop against which events occur. It is woven into the fabric of space itself, bending and stretching with matter and motion. The universe does not simply exist in time, time exists within it. The cosmic microwave background is the oldest light in the universe, and it fills all of space. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was so hot and dense that light could not travel freely. It was constantly scattered and absorbed. When those first atoms formed, suddenly light could travel, and it did, in all directions, filling the entire universe with a warm glow. That light is still traveling today, almost 14 billion years later, but the expansion of the universe has stretched it, shifting it from visible light all the way down to microwave wavelengths. It is now so faint and so cool that it registers as a temperature of about 2.7 degrees above absolute zero. This ancient light fills all of space evenly, coming from every direction. Right now, as you lie here, you are bathed in the oldest light in the universe. Photons that have been traveling since nearly the very beginning of time are passing through the room, passing through you, carrying information from an era before any star existed. You cannot feel it, you cannot see it without specialized instruments, but it is there. The universe is whispering its own earliest history through you, constantly, without pause. Planets can exist without any star at all, drifting alone through the dark between galaxies. When solar systems form, not all the material gathered around a young star ends up in stable orbits. Some objects get ejected by gravitational interactions with larger planets. Jupiter-sized worlds can be flung outward from their home solar systems, sent tumbling into the deep space between stars. These are called rogue planets or free-floating planets. They wander alone through the galaxy, not orbiting any sun, not illuminated by any light, drifting in perpetual darkness. Estimates suggest there may be more rogue planets in the Milky Way than there are stars. Some models suggest each star-forming event produces on average more ejected objects than retained planets. That means the galaxy may be full of dark, cold, lonely worlds, each one the size of Jupiter or Earth, or perhaps something in between, traveling silently through the dark, far from any warmth. And yet even these worlds are not entirely dead in a chemical sense. Some rogue planets with thick hydrogen atmospheres might retain enough internal heat from radioactive decay in their cores to maintain liquid water or other conditions somewhere deep beneath their surfaces. Even in the most isolated and lightless places in the galaxy, the possibility of something is never entirely zero.
The universe has no center that we can point to. This is one of the more difficult ideas to hold in the mind because everything in our everyday experience has a center. A room has a center. A city has a center. Even a storm has a center. But the universe does not work that way. When astronomers say the universe is expanding, they do not mean it is expanding outward from a central point into surrounding empty space. They mean that space itself is expanding everywhere. Every point in the universe is moving away from every other point, like dots on the surface of a balloon being inflated. If you were standing in a distant galaxy, you would see our Milky Way moving away from you, but you would also see every other galaxy moving away. You would conclude, as we do, that the universe is expanding outward from your location. Every point in the universe can be thought of as the center because the expansion looks the same from anywhere. There is no edge, there is no central point, there is no special location from which the cosmos radiates outward. The universe is everywhere at once, with no preferred position and no outside. That is a thought that, if you hold it gently, can feel quite freeing. There is no outside looking in. You are not on the periphery of anything. You are, in a sense, exactly where the universe is. Pulsars emit such regular pulses that they were initially thought to be signals from aliens. In 1967, a graduate student named Jocelyn Bell was working with a radio telescope in Cambridge when she detected a strange repeating signal. It pulsed with a regularity that seemed almost artificial, like a precisely timed beacon. The pulse period was 1.3373 seconds, and it varied by less than 1 part in 10 million. The team initially jokingly called it LGM-1 for Little Green Men. The explanation, when it came, turned out to be something even stranger than an alien signal. The pulses were coming from a neutron star, the collapsed remnant of a supernova, spinning extremely fast and sweeping a beam of radio waves across the sky with each rotation, like a cosmic lighthouse. These objects, now called pulsars, are among the most precisely regular phenomena in the known universe. Some have periods so stable that they rival the most accurate atomic clocks on Earth. They simply spin, sending out their pulses into the dark, far more patient and regular than anything human hands have ever built. The universe, it turns out, had already invented timekeeping long before we thought to try. Galaxies were born when clouds of gas slowly gathered under gravity over hundreds of millions of years. After the Big Bang, the universe was not yet divided into the structures we see today. For many millions of years, it was filled with a relatively smooth, slightly uneven fog of hydrogen and helium gas. The uneven parts mattered. Where the gas was very slightly denser than average, gravity was very slightly stronger. That meant those regions slowly, imperceptibly, drew in more gas from their surroundings. Over millions of years, the denser regions grew denser still. Eventually, within these gathering clouds, smaller pockets collapsed and ignited. The first stars were born. They were probably very massive and burned fast and hot, living only a few million years before exploding and seeding the surrounding gas with heavier elements. Over hundreds of millions more years, these enriched gas clouds collapsed again into new generations of stars. The process repeated. More elements formed. More generations of stars lived and died. The galaxy as we know it, with its hundreds of billions of stars, its spiral arms, its central concentration of ancient stars, was the result of this slow accumulation happening continuously over billions of years. It was not designed, it was not planned, it was the natural result of gravity working patiently on slightly uneven matter for an immense amount of time. Every galaxy in the sky is a slow poem written in gas and gravity and time. Atoms are almost entirely empty space. If you could somehow zoom in to one of the atoms in your hand, you would find a structure almost incomprehensibly sparse. At the center of an atom is a nucleus containing protons and neutrons bound tightly together. Around it, at enormous relative distances, electrons occupy a kind of cloud of probability. The nucleus of a hydrogen atom were scaled up to the size of a marble. The electron would be orbiting roughly 1 kilometer away. Everything in between would be empty. The atoms in your body, all of them, are almost entirely empty space. The nucleus of each atom occupies only about 100,000th of the atom's total volume. The solidity of the world around you, the feeling of a floor beneath your feet, the hardness of a table, the warmth of a blanket, none of it comes from matter actually being dense or solid in any absolute sense. It comes from the electromagnetic forces between atoms repelling each other, preventing them from passing through each other. You are not solid. The universe is not solid. It is a vast, mostly empty space, structured by forces so fundamental we have never seen through them to anything more basic. And yet it feels real, warm, present, here. Cosmic rays from distant supernovae pass through your body constantly.
High above the atmosphere, the Earth is constantly being bombarded by particles traveling at nearly the speed of light. These are cosmic rays, mostly protons and atomic nuclei, accelerated to enormous energies by supernovae and other violent cosmic events, and streaming through interstellar space in all directions. When they hit the Earth's atmosphere, they produce cascades of secondary particles that rain down through the air. Some of those particles, called muons, reach the surface and pass through everything, including you. Right now, approximately 10,000 muons are passing through your body every minute. They are harmless. They interact so weakly with matter that they pass straight through you, through the floor beneath you, through the rock below that, and out the other side of the Earth without disturbing anything. You are, at this moment, a participant in a process that connects you directly to the death of distant stars. Particles forged in the shock waves of ancient supernovae are passing through your body as you rest, as they have been passing through every living thing on this planet for as long as Earth has existed. The universe is not distant. It is always already here, moving through you.
Interstellar space contains complex organic molecules, including some similar to those found in living things. For a long time, scientists assumed the chemistry of life was unique to environments like Earth's surface, where liquid water, moderate temperatures, and chemical complexity could develop over billions of years. But observations of interstellar space have found something unexpected. The cold, thin gas clouds drifting between stars contain complex organic molecules: formaldehyde, ethanol, amino acids, the building blocks of proteins. Radio telescopes have detected over 240 distinct molecules in interstellar space, including some that are key components of the chemistry of life as we know it. This does not mean life exists out there in those cold clouds. The conditions for actually assembling living systems are much more demanding. But it does mean the raw ingredients are not rare. They drift through the galaxy in enormous quantities, accumulated in clouds, deposited on comets, delivered to young planets by impacts. The chemistry of life is not an unlikely accident requiring extraordinarily special conditions. It appears to be a natural tendency of carbon chemistry under a wide range of circumstances. Life, or something reaching toward it, may be the universe working out its own most natural tendencies. The night sky, as seen from Earth, is one of the most unique views in the universe. Humans are, as far as we know, the only beings who have looked up at the night sky and wondered about it, who have mapped it, told stories about it, built instruments to understand it, and sent machines to explore it. The particular view we have is shaped by where we are. We live in the outer spiral arm of a galaxy, far enough from the crowded, radiation-heavy center to have a relatively stable environment, but still within the Milky Way's disk, which stretches across the sky as a faint band on dark nights. Our moon is large enough and close enough to cause tides and stabilize our axial tilt, which moderates our seasons and climate over long periods. Our sun is a calm, middle-aged star, not prone to violent outbursts. All of these circumstances combined to create a window, a period of stability lasting billions of years, during which life could develop, evolve, and eventually produce creatures capable of looking up and asking where they were.
The night sky is not just beautiful. It is evidence that the conditions for wonder are not infinitely common. And it is evidence that those conditions, when they arise, can lead somewhere extraordinary. The elements in your body were scattered across the galaxy before they gathered into you. The iron in your blood was not always on Earth. It was not even always in this solar system.
Some of it was made in supernovae that exploded billions of years ago, perhaps in entirely different regions of the galaxy. The shock wave from those explosions dispersed the freshly made elements into the surrounding interstellar medium, where they drifted for millions of years, mixed with gas and dust, until eventually a new cloud began to collapse. Our solar system formed from such a cloud about 4.5 billion years ago. The heavy elements scattered by generations of dead stars became part of the disk of material surrounding the young sun. They accreted into planetesimals, then into protoplanets, then into Earth. Over billions more years, those elements cycled through oceans and rocks and early single-celled life, through ancient seas and continental interiors, through the bodies of countless organisms that lived and died before anything resembling a human existed. And at some point in the last few billion years, in a process we do not fully understand, some of that matter became capable of sustaining life, became you. You are the universe's matter, gathered, organized, and made briefly aware of itself. When you breathe out, you return some of it. When you eventually return to the ground, all of it. You are made of borrowed atoms, as is everyone. Some stars are so large that, if placed where our sun is, they would extend past Jupiter. Our sun is not a small star by any measure. Its diameter is about 109 times that of Earth. 1 million Earths could fit inside it. And yet there are stars that make the sun look modest. The largest known stars, called hypergiants or supergiants, can have diameters several hundred to over 1,000 times that of our sun. Stars like UY Scuti or Stephenson 2.18 are so enormous that if placed at the center of our solar system, their surfaces would extend past the orbit of Saturn or even further.
These stars are not stable in the way our sun is. They are burning through their fuel at an extraordinary rate. What might take our sun billions of years to consume, a hypergiant burns through in a few million. They are brilliant and short-lived by stellar standards, destined for dramatic deaths as supernovae. But for the time they exist, they are the largest individual things in the universe. Not the most massive, not the most energetic, but the largest in terms of simple physical size. Objects so large that our entire solar system, everything that has ever been meaningful to humanity, would fit within them. The universe is mostly quiet, but occasionally something extraordinary interrupts the silence. Most of the universe, most of the time, is doing nothing dramatic. Stars burn steadily, planets orbit, gas clouds drift. The expansion of space continues its slow acceleration. But occasionally something remarkable happens. 2 neutron stars, each the compressed remnant of a dead star, can spiral slowly toward each other over billions of years, brought together by the loss of energy as they emit gravitational waves. Eventually, they merge in an event called a kilonova. In those few seconds of collision, they produce more gold than exists in the entire Earth, along with vast quantities of other heavy elements. The collision also sends ripples through space-time itself. In 2017, gravitational wave detectors on Earth detected the signal from just such an event, 2 neutron stars colliding 1,600 light-years away. For the first time, humanity heard space-time vibrating. Or consider gamma-ray bursts, the most energetic explosions known in the universe. Some release more energy in a few seconds than our sun will emit over its entire 10 billion-year lifetime, They are visible from across the observable universe. The universe is quiet most of the time, but when it is not, it is spectacular beyond any scale we carry within us. Stars are born inside cold, dark clouds, and the process takes millions of years. The places where stars are formed do not look dramatic from the outside. They are cold, dark clouds of gas and dust drifting between the stars. They block the light from anything behind them. They are among the coldest places in the universe, sometimes only 10 or 20 degrees above absolute zero. But inside them, something is always beginning. Where the cloud is slightly denser, gravity slowly wins. Matter begins to fall inward imperceptibly at first. Over hundreds of thousands of years, a core forms and grows. As it compresses, it heats. Eventually, the center becomes a glowing protostar surrounded by a disk of material.
Over millions more years, the protostar heats and condenses until the core reaches the temperature and pressure needed for nuclear fusion to begin. A new star ignites. Somewhere in our galaxy, this is happening right now. In quiet, dark clouds invisible to the naked eye, new stars are being born. New solar systems are forming. New planetary surfaces are being shaped by heat and impact and chemistry. The universe is always making something new. It never stopped. You share atoms with everyone who has ever lived. The atoms in your body are not yours. They were never yours. You borrowed them from the world, and eventually you will return them. The oxygen you breathe is released by plants and absorbed by countless living things every day. The water in your cells has cycled through clouds, rivers, oceans, and countless other organisms over billions of years. The carbon in your tissues was once carbon dioxide in the air, drawn down by photosynthesis into leaves, eaten, transformed, exhaled, and recycled again. Some of the atoms in your body were, at some point in history, part of the ocean during the Cambrian explosion. Some were part of the atmosphere when dinosaurs were alive. Some traveled through the bodies of ancient bacteria that existed before complex life evolved. And some, with statistical certainty, passed through the bodies of other humans, through ancestors you never knew, through figures from history, through ordinary people who lived and died in quiet obscurity long before any record was kept. The substance of who you are is shared with all life that has ever existed on this planet, and before that it was shared with the stars. As we come gently toward the end of this journey through the cosmos, you can let the facts and images you have encountered begin to settle, to soften, to become less distinct. You do not need to hold them. They will still be there, woven quietly into how you understand the world around you when you wake. Picture the universe as it is right now while you rest. Billions of galaxies, each containing billions of stars, each star burning steadily in the silence. Ancient light traveling through the darkness, crossing distances so vast that the mind simply releases them rather than hold them. Rogue planets drifting alone in the deep between stars, pulsars spinning their steady pulse into the dark, cosmic voids so vast and so empty that nothing much disturbs them for hundreds of millions of years. And on one small, warm planet, orbiting a calm, middle-aged star, in an outer arm of one ordinary spiral galaxy, you are resting, still, quiet, connected to all of it by the atoms you carry, the light that falls on you,
the ancient cosmic background radiation passing through the room. You are small in the universe, and the universe is gentle with small things. It has been making space for life for billions of years. It made space for this planet. It made space for you. There is nothing you need to do right now. The universe will continue its long, patient work without any help from you tonight. You can simply rest. Let your body settle. Let your thoughts become like distant stars, present but soft, asking nothing of you. The cosmos is vast, it is old, it is mostly quiet, and right now it is holding you. Sleep well. Good night.